So welcome back, everyone. It is March 17th. Welcome to our next Water, Wetlands, and Watersheds seminar. This week, we are lucky enough to have Dr. Sam Zipper with us. He's zooming in from Kansas. Sam, I'll give you a little intro here, and then the screen will be yours to share. So Sam Zipper is an assistant scientist at the Kansas Geological Survey, so that's the KGS. And KGS is a research and service unit of the University of Kansas. So it lives, it's sort of a subsidiary of the University of Kansas, not officially associated with the USGS, but they do work with the USGS. So at the KGS, he leads something called the Hydroecology of Anthropogenic Landscapes group, or the HEAL at KGS. And their goal is to understand how local, regional, and global change will affect water resources in Kansas and the Great Plains now and in the future. Sam's originally from the Seattle area. He did his undergrad in geology at Pomona College, which is in California, I believe, and then did his PhD in freshwater and marine sciences at University of Wisconsin at Madison. He spent a few years ambling around Canada and then joined KGS in 2019, specializing in hydrogeology and eco-hydrology. And so today we're going to hear, I think, a lot about landscapes that go dry from time to time and why it's actually cool. Like, this is the water and wetlands seminar, but we invited him anyway because sometimes going dry is actually super critical to the ecological function of an aquatic ecosystem. So Sam, the floor is yours. You can go ahead and share your screen.
All right, well, thanks a lot for the intro and the invitation to be here. Let me get this, let's see, pulled up on here. Oh, didn't have the highlighter. There we go.
Yep, we can see it.
Perfect. So yeah, two, I guess, technical notes up front. About every half hour, my home internet freezes for 5 seconds. So if that happens, I'll be back, and I'll try to notice when it happens so I can stop talking for that period. And secondly, I mentioned to David that there's some young children in the house right now. So if there's a ruckus, just bear with it. They all like non-perennial streams too, so it's all part of the family fun. And yeah, today I'll be kind of sharing some work at two very different scales, some national scale and some more reach scale investigations of what causes flow and what causes change in flow in non-perennial streams. Oh, there we go. By brief way of introduction, I know there's kind of students in this course, so I wanted to share a little bit about the State Geological Survey lifestyle, because it's, I would say, a career path I wasn't particularly aware of. What's really nice is I have what's considered a faculty equivalent position, but instead of a teaching responsibility, my charge is basically to work with state agencies in Kansas for water-related issues. So, that includes the Kansas Water Office, Division of Water Resources, as well as stuff you might not think of, like the Department of Transportation and things like that. So for people interested in kind of, I like to call it the interface of basic and applied science, I really think geological surveys are great places to work, and Florida has a good one. So I just wanted to give a little shout out there. But yeah, like David mentioned, my goal in my work is to try to understand how various drivers of change can and will affect Kansas's water resources. I do that in three sort of focal areas. One is really investigating agricultural irrigation and how water conservation can impact groundwater and surface water resources. And I won't talk much about that today. Kind of the focus today is going to be on sort of these two categories on the right. The first is ephemeral hydrology. So playas are Kansas's ephemeral wetlands. They are perhaps different from Florida's in that they tend to be very disconnected from the regional water table. So they're perched over quite a thick vadose zone. We won't talk about those today, but we will talk about non-perennial streams and stream aquifer interactions, which is kind of my main sort of disciplinary, I guess, expertise, you could say. And many of you may not care about non-perennial streams. I too once did not care about non-perennial streams, but now I do, and I'll share three reasons why I do. The first is that non-perennial streams are quite widespread. By some estimates, they make up more than half of the global stream network, and in dry regions like Western Kansas or New Mexico, which is pictured in David's background, they can be the large majority of the stream network. A second important point is they provide a wide variety of different ecosystem services. So both ecosystems and society rely on these non-perennial streams. And interestingly, in contrast to the perennial water bodies that we typically think about, they can provide a real diversity of ecosystem services due to the fact that sometimes they're flowing, in which case services provided may include, food or recreational fish provision, but sometimes they're dry, in which case they can provide very different services associated with, for example, infiltration, flood reduction, and providing freshwater supply. So they've got a wide variety of different functions in the landscape and for society. And, for better or for worse, they're becoming more common. So over about 60 years, towards the end of the 21st century, just trying to keep my century straight here, an estimated 9 kilometers of perennial streams in the Great Plains transition to non-perennial streams per year. So they're becoming quite a bit more widespread. Again, for better or for worse, that can kind of trigger trade-offs among the services provided during the flowing state to sort of ponded or dry state. But relative to their importance, non-perennial streams are quite understudied. The field of hydrology has been founded on and historically focused on water that flows, though there is a lot of kind of energy towards non-perennial streams right now, which I'm really excited about and happy about. So today we're going to cover 2 different analyses or studies, both of which are very much in kind of the development stage. So feedback and questions and criticisms are quite welcome. The first part, we'll look at the broad scale, the national scale, to figure out how and why is flow in non-perennial streams changing. And then the second, we'll zoom into the specific non-perennial stream here in Kansas and try to figure out what's controlling flow in that specific reach. So to start off with, we're going to look at the national scale. And here I'm going to investigate 2 questions. The first one is quite descriptive. How has stream intermittency changed over the past 40 years across the continental United States? And then the second is more exploratory, which is what are the drivers of the change that we observe? And this is work that comes out of the Dry Rivers Research Coordination Network, which is led by Dan Allen and Katie Costigan. And this is, I would say, a group that's really kind of responsible for a lot of energy around non-perennial streams right now, as well as counterparts in Europe and Australia. And this work was done as part of this collaborative working group, and a lot of people contributed to the stuff that I'm going to be sharing today, in particular, some of the names that you'll see here. So what we did was we took the U.S. Geological Survey's entire gauging network, and first we identified which are the non-perennial gauges. So what you're seeing mapped here are within the continental United States, all of the gauges that average at least 5 no-flow days per year and have at least 30 years of data during the past 4 decades. So you can see that there's a lot of gauges in some regions, for example, California, Texas, the Southern Great Plains. There's also some very conspicuous gaps, for example, the state of Nebraska. So I do want to point out, this is not a map of where there are non-perennial streams, rather where there are gauged long-term non-perennial streams. And gauging decisions are driven by, state and federal decisions related to water supply. So there are non-perennial streams kind of in every state on this map. And what we then did was took the annual hydrograph for each of these gauges during that 30 to 40 year period of record and extracted 3 hydrologic signatures, which are just ways of distilling the hydrograph into a single value. So the first one is the duration of annual no-flow conditions, and we quantified that as the number of days where there was 0 flow readings at the USGS gauge within each year. The second is the rate of drying, or the dry down period. So that was the amount of time it took for the stream to go from its peak to the first onset of no-flow conditions. And then the timing of no flow within the year. So that was the date at which the first no flow event was observed within each year. Just a quick methodological note that these were all done based on the climate year beginning in April 1. So day 1 in these analyses were April 1. And we then calculated each of these 3 hydrologic signatures annually for each one of those 540 days. Large data set of stream intermittency. And with that data set, we then performed a few analyses, which I'll dig into 2 of them here. The first one is a man-Kendall trend test, which is a way of looking at the direction of change through time. And the second is using random forest modeling to try to infer what some of the drivers of change might be. So the first step was looking at trends. So I'll show 3 maps here, which is why this top one's a bit small, because we're going to fit 3 of them on here. But in each of these maps, we've got 1 dot for each one of those 540 stream gauges. If that dot is filled in, that means there was a significant trend at that gauge. And if the color is more red, that means it's a drying trend. So in the case of annual no-flow days, a red color would indicate a trend towards more no-flow days within a year. And what we found, just looking at the duration of annual no-flow within the year, we found that 40% of the gauges had a significant trend of one direction or another. So these changes are very widespread. And the majority of those were towards drying conditions. You can see in particular, those red dots are kind of clustering around the south and west, though Florida does have a few. So there does seem to be some kind of regional patterning in these trends. If we then look at our other 2 metrics, so this middle map is the number of days from the peak to no flow. So that gives us that kind of rate of drying, or the dry down period. And then the third map is the timing of the first no flow day within the year. We can see some similar patterns, but less significant change. So for the middle plot, we've got 15% of gauges had a significant trend in one direction or the other. And for timing, 14% of gauges had a significant trend. And for both of these, the majority of those significant trends were towards drier conditions, which would be indicated by faster drying and an earlier onset of no-flow conditions. And if you look at all 3 of these metrics, we found that half of those 540 gauges were experiencing at least one significant change related to stream intermittency over the past 4 decades. So these changes are very widespread. As I mentioned,